engineering from Polytech Engineering School in France in 2018, and then I moved to the UK for my graduation, for my master's degree, where I was graduated in 2021. I did my mechanical engineering in the University of Leeds, and since then I'm enrolled as PhD researcher at Warwick University. My focus is on lithium-ion batteries. I will talk about what I'm working and how we can improve the lifetime or longevity of lithium batteries for different applications, but I will focus on electric vehicles. During my research career, I worked for a few weeks to few months in different organizations in different across the world, but mostly I spend my time in Europe. I started research assistantship in Medical University alongside my education in the UK. So I worked there as a cathode scientist, synthesis of cathode from raw material from wastage of electric arc furnace or different furnaces. There is a huge amount of consuming these metals and converting to different useful products. So we were focusing on converting those metal powder into cathode, which is a major component in batteries. And in 2021, I worked for in Aachen RWTH, which is very well known for recycling of batteries. So using spent batteries into and converting into useful products is also a major challenging these days, because we have batteries everywhere, even starting from smartphone, remote cells, and in big gigabytes industries, for example, in electric vehicles. So we can't. I will speak about how we can use the. So basically, we can't use the batteries in electric cars if the life cycle is less than 80%. So if it faded to 80% after a few certain time, we have to consume or recycle the batteries, which is this is why people are working on recycling. And I'm also affiliated with Diamond Synchrone facility in the UK in Harwell campus. So where we do some analysis, surface analysis, what is going on in batteries when it cycles at certain voltage and different. I will speak about later. And also I work as a researcher for coating the materials, which is useful for why we do coating. I will also speak about later in Coimbra in Portugal. So this is a very, very, very complicated diagram. This is very deep into science, what is going on in lithium-ion batteries. And this is just to show you, just to confuse you guys, what it has and we are working on as a research, as a battery scientist. We are working on very, very deep into very, very atomic level or micro level in the batteries. I will speak about what is this about. So my current topic of my talk is to how we can improve the life cycle and longevity of lithium-ion batteries for commercial available cathodes. So I divided my talk into three different segments for introduction and background, and then I will speak about manufacturing of battery and different types of cells and safety issues involved with lithium batteries or battery cell. So this is how battery cell works. So we have the cathode, which store lithium ions inside. This is the major component in to have lithium inside battery, inside cell. So when we charge, we push the lithium ions or extract, and it goes toward, it has to go somewhere or store somewhere. So when we charge, the ions move towards anode. Anode is graphite or could be any other material, and it's passed through the separator. So we have different types of separators, but mostly usable is polymers for lithium batteries. And so then when we charge, it goes to anode, which is made of graphite, and it has the structure of, if I show you the structure is honeycomb, so which can have lithium ions into its sides. So then when we use, meaning we discharge the cell, it goes back to the cathode. And we also, so the movement of ions is, we should have electrolyte, which is a liquid solution, or salt which contains dissolved salts or solvents into it, which allows which aid the movement of the ions from cathode to anode. So concerning the cost in lithium-ion battery components, the major portion is consumed by cathode. Again, because there are reasons, but major reason is stored lithium inside. So it also made by different transition metals. There is a huge science how it made, but major component is which consume more cost is cathode, followed by manufacturing and other labor cost. So when we talk about cathode, we need to consider raw material and how we can produce production cost. So we are working in the UK. We are working to use cheap material or cheap metals and giving high capacity or giving the high density. So this is something we are working on, using this, maybe the raw use or recycled material, or very less expensive or inexpensive raw materials. And like I said before, it's going to be very deep into when we do talk about research. Nickel-rich cathode is another factor. Nickel, when we speak about nickel-rich, it has nickel. Major component of major element transition metal is nickel, which is could be 90% or 80% or different ratios. But we use nickel because it's less expensive. It gives high energy density because we can extract lithium from the structure easily, and it can be consumed for a long time, and it's not toxic. When we use cobalt, because which comes from Torongo, it requires it. The major issue is not only cost; it also toxic to the air or to the environment. This is why we are working to make it less toxic but high efficiency. And there are different layer structures. So like I said, the nickel gives us high energy, less cost, durability is longer, and the power is also completely, which satisfies our demands. And the other structure is lithium rich. Lithium rich it gives high capacity, but the cyclability is very low. This is lithium rich, which means the battery will fade fastly. But of course it has lithium rich, more lithium, but we have high power. So, and the third is spinel. Spinel is like it is less expensive. The good example of spinel structure is LFP. LFP contains iron. We replace nickel with iron, it makes spinel structure. So it is less expensive, but the issue is we can't have high power or energy. So we will majorly these days we are working on nickel-rich materials. Another another fact, like I said before, if we use nickel, we have higher capacity. Higher capacity means practical capacity when we use in commercial cells. But yeah, so increasing nickel contents, we have higher capacity. But the issue with nickel-rich system is when we charge or discharge, it expand and contract. The structure inside the battery, it expand and contract. That means we have cracks at surface or cracks at the cathode level. So the cracks can generate gases into the battery cell. Gases is a very, very dangerous issue. When you have gases, that means carbon dioxide or carbon monoxide, that swells the cells and we can have explosion in battery sometimes. I'll speak about what safety concerns are related to those things, but major is when we have gases generate in the cell, it will explode. So these explosion comes from when we expand the structure of batteries. So expansion and contraction happen when we extract lithium, it expands because of the different ions, same ions at the cathode. So which of course causes cracks at surface, and so this is major concern with nickel-rich system. So that means if we increase the nickel content, we have capacity retention because of these gases and cracks happen at surface. So the research community is working to improve the nickel-rich cathode. This could be by doping. Doping is doping with different elements, transition metals. First, the good example is tungsten or aluminum. Tungsten is and aluminum, they are cheaper and they don't fail the capacity or the energy density, but they stabilize the structure. The stability comes from because aluminum is conductive. It can stabilize the structure into when we cycle. And this is the figure you can see at high voltage. 4.3 is high voltage when we speak about laboratory scale. So you can see the figure discharge capacity comes down after 5,500 cycles. But if we don't dope, without dopant, nickel rich, they fade it fastly after certain cycles. And the second is coating. We can also coat with different materials. First example is alumina. If alumina is Al2O3, it stabilizes again the surface. That means we don't have oxygen or gas release in the battery. It not only improves the cycle stability but also improves the gas evolution in the cell, which means we can make it safer and have high energy. So this is very, very thin film at surface, like 10 nanometer, which we can't see even with eyes. This is done by different coating techniques. So these two strategies which can be utilized to improve the cycling and of course the safety. So in Tesla, we also use the nickel-rich material. So they improved the stability, life cycling, and energy density using the aluminum. So that means we can, even the commercially available cells, with Tesla, which gives you 500 mileage from if it fully charged. So they also use aluminum to improve the long cycling stability in commercial cells. So here is the example. Again, another example which we've done in our lab in WMG. So what we've done is we cycle LNO, and LNO is only nickel in the battery, nickel oxide which is made to make cells. So like I said before, if we use high nickel content, can fade the capacity after certain cycles. But if we have to stabilize, we have to use different dopants, which is the dopants could be aluminum, or here we use manganese and cobalt, very small quantity, so that you can see the stability is very high compared to non-use compared to non-doped or non substitute metals oxide at high voltage. So again 4.4 is high voltage when you consider a small scale or small cells. So now I will speak about manufacturing process of EV battery pack, EVs, electric vehicles. So majorly we are working on high EVs in the UK to improve. If we can improve the big application, we can of course improve the small cells. So we can, if we have higher energy density batteries, we can improve the we can reduce the fuel consumption. That means environmentally safe, and we can even decrease the cost of fuel. So that means if we consume 100 miles, like 30 pounds for 100 miles, we can charge in 6-7 pounds to use the same mileage in EVs. This is why we are in the UK. The government is working on batteries and to reduce the oil or fuel consumption in the daily transportation. So how it works is we have raw material from minings. The major source of mining is in Bolivia, Chile. They have they extract from seawater. They have lithium enriched minerals in their country. So we get minerals, raw materials, which we make battery cell. Then we assemble the cell. I will show you how it looks like. And then we manufacture EV, electric vehicles, and then sell out and then lastly we do recycling. Recycling is also very important in terms when we use battery. 80% of battery, less than 80% its capacity is not usable for EVs. So this is why each electric manufacturing EV company, they give warranty of almost 8 years, 6 years. For 6-8 years, it will not degrade to less than 80%. So if it degrades to less than 80%, we do recycling or use the same batteries for our solar panels at home, or we can use it as energy storage batteries, as second life battery for different purposes. These are three major types of cells which we use to assemble a battery pack for electric cars or electric vehicles. So cylindrical cells, power cells, prismatic. So they have drawbacks and advantages. But cylindrical cells is cost efficient, which we use. Even these cells we use in the remote control for our different in our daily applications. But you never saw maybe in power cell. Power cell is a cell which we can use in our batteries of smartphones. It makes a roll which is assembled differently. And prismatic cell. Prismatic cell is mainly used for battery packs or in industrial aircraft, because it's with small cells we have high amount of energy to store, and it delivers more energy and power. This is something battery pack looks like for EVs, for electric cars. This is the bottom side where you so these cells are assembled differently. It could be or cylindrical cells. This is how it looks like. It's very heavy. Main component for electric vehicle. So some safety issues for lithium-ion batteries. We have to consider the safety issues. So firstly, it revolves around thermal runaway. The thermal runaway it happens when we use the battery which can't extract lithium. Which can't extract lithium, it makes the batteries very hot. So that means if we don't manufacture the cells, good one, it will create issues, and also some anode plating, cathode plating. So this is I will explain how it happens. Anode and cathode plating is when you charge, the lithium ions won't extract it, but they form a long plates. This is called lithium plating. And lithium plating is very needle-like structure. Needle-like structure goes into the cathode side and make a circuit short. When you have short circuit, you can generate heat into the batteries, which eventually explode and causes fire. What process involves when we have accidents caused by battery failure? Battery failures they have different types. For example, at car level, pack level, and cell level. At car level, a driver won't know what is going on. It happens within few seconds or few minutes. The car level, which audience and everyone is going through. If you see any explosion, maybe never saw, but if the car catches fire, you see what is going on around. So this is car level battery issues. So fire brigade and everyone audience is looking at it, or the people are around by. So in pack level, the manufacturers or the companies who made the cell, they look at what is the major cause, or how this happened, how explosion happened. They look at pack level. If there was assembly issue, or it was something happened with leakage. The leakage is major issue for explosion of batteries. If leakage happened, that means battery cell will get oxygen or different air which react with electrolyte, and electrolyte is a acidic solution during cycling it generates high amount of gas which will cause explosion. So cell level, which we or scientists see what is the major issue, either it's cathode, anode, or something happened which during the assembling of cells, during the assembling of different components within the batteries. So this is what we look at. And if one cell catch fire, it won't stop. It will explode everything because of heat generation and gases. These are real life examples of explosion of Tesla car happened a few years ago, and you can also have some thermal runaway into your battery cell. It can. So this is a real example of how gases generates, and if gases generate, if you just pinch it a little bit, or if it's scratched, it will explode because of the reaction with environment or oxygen. So coming back to the battery degradation picture. So a little bit of what happens is when you have, this is lithium plating, it has needle-like structure. When we can't extract lithium completely due to, could be any issue, maybe the lithium was not good, or when we charge and there's some circuit issue, that forms a lithium plating. It doesn't happen quickly, but it requires certain time or different, the same hazard happen again and again, and it will tear up the separator, which is a barrier between cathode and anode, and touch the cathode, which will cause short circuit or explosion of batteries. And there are other factors which can cause this. For example, this is decomposition of layer at it naturally forms a layer at surface of cathode and anode. If it breaks down, we can also cause these short circuits at different levels. So this is the complete and very famous picture of battery degradation or safety concerns. And yeah, thank you very much for your time, and I would like to acknowledge my institute and Faraday institution, which funded me to be here and speaking with you nice people.
Are there any questions? Can you hear me? Yeah?
I've got about 3 questions, sort of probably elementary as far as you're concerned. If you get, everybody can hear.
All right. Yeah. If you do get a fire in a car, obviously the natural reaction is to get out of it and run like mad. What did the fire service do? How did they? What's their sort of strategy for dealing with these? Do you know?
Yeah. So you mean if they have car fire?
Yes.
So firstly, so they have some cars. Recently, they introduced a cooling system, which is automatically if it explodes, it won't get off, and there is a cooling like water or any other solvent which can reduce the fire issue to be explode much. So yes, this is the first thing they have in. But if the fire is already made itself, if you can't just control the fire, or you can't stop it.
They've just got to leave it to burn itself out, basically.
Yeah, but again, they are introducing a cooling system, which will allow the stoppage.
And that standard is it across sort of all car batteries? Is it?
This is Tesla or Chinese company.
What about others? I mean, not all others can afford Tesla cars for a start.
So I also drive electric car, right? By the way. So these days, before they introduce the car to the consumer or customers, they test it for several days. The battery goes the cycling process, charge and discharge. If any concern happens, they will change the battery back.
Yeah.
But to be fair, any hazard can happen anytime you might be a fuel car.
Yeah. Second question, I think probably almost answered it, but in garage charging, and I never charge my car inside the garage, partly logistics, but I would have thought that's not a sensible thing to do anyway. Is there any recommendations on that? Should you always charge it in the outside world?
Yeah, so you can charge it. So the issue happens is if you have any damage on the bottom of the car,
Yes.
that can pinch or scratch the battery pack. So anything leakage, when leakage happens, as long as not any leakage happens, it's safe to charge anywhere.
Right. So it's okay outside.
Yeah,
Yes.
Even inside the garage or outside, it's totally fine. It's safe to charge.
And the final thing was charging speed. What governs that? Because obviously the Teslas take on a lot of charge very quickly. Others don't.
Yeah, so the charging factors is you have different. So when you push the electrons of when you charge it, you give an energy push to extract the lithium ions. If you charge it at home, it takes like 24 hours to get it full. But the main issue is they are developing a material which allows the fast removal of ions, of extraction of ions. When you have fast extraction of ions, it charges fastly.
Yeah.
So it depends on, for example, if I give you how it looks like. So this thing is they are improving because all lithium when you extract they comes here and sit into the anode side. Anode is a honeycomb structure. If you can improve the structure, the size of lithium will be there. So this is why if you this can lead to fast charging.
Thank you very much.
So it doesn't matter about the cathode, the charging speed
It also depends, but again, majorly because when you charge, you extract lithium. You extract lithium, it should be stored somewhere. So the more storage, or it can also loss. You can have loss of lithium. This is why you have fading of capacity after 1 year or 2 years. So if your cathode is not good, it will not come back again. So both sides should be, but majorly anode during charging.
Hello. I have a number of questions also about charging EVs. Most manufacturers of EVs these days, one of the key parameters that they sell their EVs on is the ability to charge the EV from 10% to 80% in less than a half an hour, typically. You've actually got to use a DC high power charger, which are very, they're available, and those push something like up to 350 kilowatts into the battery. My question really is, how does that affect the degradation of the battery if you were to charge your EV every time up to 80%, up to 100%, using a high-powered DC charger at 400 volts? How does that affect the degradation of the battery in the vehicle over treating the battery gently and charging it on a 7 kilowatt home charger every night over a 4-hour cycle? That's the question.
Yes. So again, it's if you charge as fast rate will also allow the formation of layer on cathode and anode side. So the fast charger, so there is natural layer form at cathode and anode surface when it cycle. If you do fast charging, again it will break down the surface. Oh, sorry, the layer. The layer is called cathode and anode interface plates. So or in electrolyte interface. So when you do fast charging, you remove that layer time to time. If you remove that layer, that means you are at a point where you can use only, for example, 500 will degrade will fade to 200 mileage. So this is why this leads to, if you can charge 100%, but the mileage or outcome would be less. So that means to cure this issue, they are using the layer which is very, very thick and barrier to these issues. This is why they also, if they are producing high voltage like 140 or 300 kilowatt, the material is different. This is why you also, so even if you go to Tesla charger, they give an output of 140 kilowatt. So, but the Tesla material is different. They are protecting the surface. And but if you're using the small voltage like 7 kilowatt, you can use this for 10 years, 15. So I know a person who is using Nissan Leaf since 2011, and he said, since 2011 it never faded. The same performance I'm getting when I bought, because he never used more than 40 kilowatt charger, and we just use 7 mostly at home. But the major issue comes when you have break down the layer of cathode and anode.
Okay, thank you. So effectively, if a car is designed and
if we design to 400 watt, or I'm using the AC current, if for example 70 kilowatt, it won't go more than 65 or 60. It automatically they design it using research.
Can I just ask, what electrolytes do you use in the batteries?
It's it's LFP. So mostly they're using lithium phosphate, and we are using in our lab we use this LFP system, but we also add different elements or additives. So when you add different additives, it is expensive, but it also help in forming a surface layer during the charging and discharging. Again, so all is concerned about it won't degrade or decompose, because electrolyte also consume when you charge and discharge. It forms the salts, and which hinder the lithium movement. So this is also very important to use the right electrolyte.
Hello, gosh, that's powerful. Just building on the start of your presentation, which was longevity. One of the challenges is, what is the life of a car? You know, some manufacturers say it's 10, 15, some say it's mileage. I'm not sure if I've understood your objective, but it sounded like you'd like to get the battery life to be that by the end of the life, probably chronologically or mileage defined, it's still got 80% of the charge. So I was just interested, what do you define as the life of the vehicle, and is the objective to get to the battery will survive the entire length of the vehicle, i.e. the point where the vehicle itself would be declared end of life? Is that your objective?
Yes. Yeah. So it should be 80% after 8 years, 10 years, because these days Chinese companies give the 10 years warranty. If anything happens, you get low mileage up to 5 years, they will change the battery pack. And also it should be stable and doesn't contain any gas issue. So that means longevity and safety. So our objective to work, which we are working on these in the UK, is make it safer, cheaper, and long durable.
Any more questions, please? It's all gone quiet.
So your graphs, where the number of cycles are on the bottom, only went to 100 cycles. I believe if you have a Tesla, the capacity decreases by about 5% very quickly, then it's level for ages and ages. And you didn't, I don't think you said much about battery management, which seems to be the key to longevity of batteries, to keeping them cool when you charge them and things like that.
So the battery management when you charge.
Well, and when you discharge them, you've got to keep the temperatures constant as possible. Is that right?
Yes, yeah, exactly. If you have to maintain the temperature, which is why the battery designed with the cooling system itself. So cooling system maintain the temperature to 40, not more than 40 degree. So 40 degree means you can also you can mobilize the lithium ions within this temperature. The kinetics will increase, and also if you should not, there is a self-maintained also cooling system in the batteries. Should be not exceeding more than 40-45 degree, and not lower than lower you can go, but you can't just control. There is a heating batteries heating automatic battery heating system also included in the cars. So
you just do that by blowing air through the battery, or water cooling?
The water cooling system. So because battery pack is packed, they can't have the airflow into the battery, because it also changes the speed of car if you flow the car, but there is a water cooling system.
Yeah, I think the Teslas will cool the batteries while you're charging, don't they?
Yeah, yeah, it does. It does. It is. I didn't show about the cooling system because it comes with different thing, but there is all cars have cooling system.
Hello? I'm not an engineer, so I don't fully understand or I don't understand at all what you've been talking about, but it's been very impressive. But I know Toyota have set plans for something called, I'm going to read from the internet because I don't remember it. It says it includes 3 new liquid electrolyte battery technologies, referred to them as being solid state. What's the difference between that? I mean, it's not something I think which is manufactured in a general way now. They're saying in 2 or 3 years' time they can. What's the difference between that and this? They're saying it have longer range, higher power, longer lasting, everything better. What's the difference between them?
The liquid electrolyte, the difference between liquid and solid state electrolyte is we use solution, which allows fastest movement of lithium ions. But solid electrolyte, it can reduce the movement of lithium ions, but it's very safe and also long term. You can use it. Maybe they are predicting maybe use 20 years without generating any gas. So liquid electrolytes decompose and generate gases in battery cells, but with solid electrolytes you don't have any issue. So that means the cars will never have maybe 1 in billions will explode, otherwise no chance. So this is why they use solid electrolyte and for longer.
Does that mean then the solid state is the best, better technology than this?
It is better, but we can't extract much power because it doesn't. It's very slow movement. So you can use maybe in future if they change the morphology or structure of electrolyte, but it can't give much power to be used in EVs these days. Yeah, because we need high power density in EVs.
I appreciate that you're probably talking about full cycles there, but 100 doesn't seem very many in the life of a car.
Yeah. Yes. So in the lab scale, we do 100 cycles to see the performance. Initially, it reduces our time. If we do 1,000 cycles, it takes 1 year to get the result. 100 cycle takes 3 months or maybe two months. This is why we need time. We can't just rely on Apple unless we have many people to work in the future. But yeah.
And it presumably means that I read occasionally of schemes where car battery power might be used as a brief top-up for the mains. Sounds as though you would be very unwise to take part in having your battery used for that.
Yeah, I didn't sorry understand your question.
Another question down here.
versus 16 years if you're using the charging to 60% technique. Would you sort of agree or disagree with that, or could you add anything to that?
Yeah, I would say I agree, because when you charge with 100% state of charge and do 60% state of charge, so 100% means you remove or extract all the lithium from the cathode, and when you discharge, it might not coming back or not reversible. Few ions of lithium are destroyed, or they don't come back to its sites. That means each time you consume 1 or 2 lithium ions, you are destroying 1 or 2 lithium ions. So of course, with time you have less lithium ions. But if you do 60% state, you do 60% charging, that means maybe out of 100, 99.9% of lithium ions come back to its cathode where it is stored. So yeah, but lithium ions can destroy, can be lost, or anything can happen.
Any further questions? Well, I think,
So, to prevent people from putting in batteries that are twice as big as they are now, do you think there will be government legislation on the size of batteries that can be put in electric vehicles because of the extra wear on the roads and tyres and everything else?
Yeah, exactly. So it also depends on different materials they use. For example, if they use lithium with iron cathode, LFP, which is called iron phosphate, and versus lithium nickel rich or any other material. So if you see the density of the iron, it requires big packs, high packs are required and much weight. So compared to the other, so it also depends on material you use, and of course if you are using in big, even with some these days in Germany or in China, they are working to produce electric trucks. They are already commercialized. Electric trucks means complete tons of batteries inside that truck. So, but the legislation is different. They're working on different environment. But yeah, it impacts if you using different size batteries.
thank you. If I understood you correctly, it is better to charge a car battery up to 60% rather than always charge it right up to the top. Is my understanding correct?
Yes, so you can do 80%. The threshold is 80% from 0 to 10 to 80%. That will not allow all the lithium out of its cathode. So this will make your battery life longer than compared to 100%. Yeah.
Thank you for that. The follow-up question, which is really behind it, is: do you think that applies to all other appliances which have batteries and chargers? Should we be aiming to always charge them up to the top, or should we, in fact, only set a level and charge them up to there?
If I talk about the smartphones, the smartphone companies these days they don't appreciate 100%, 90%, 90, maybe 85%. It employs, because if you use lithium-ion batteries, it employs everywhere. But because we have high big volume of lithium ions in batteries in electric cars, this is why we always take into consideration. And they have different parts in different packs, so it takes all the lithium from different areas. Yeah.
If I bought a second-hand electric car, is there any means of assessing the state of the battery in that car with respect to its future life?
Yeah. So if you buy second-hand car. The first thing is maybe they change the battery pack. They give you a new, they replace the battery pack and give you a new one. Maybe if they're not, so you have to do a test drive. This is why they always encourage you to do a test drive. If you do a test drive, if you, for example, in out of always the good way of doing test drive is 40, 50, or 60 miles. If you're getting the outcome more than 3.5 kilowatt per mile, that means it's fine. And if you're getting low, like 2.5, you don't need to consider the car. Maybe this is from my understanding or from my practical and little bit of knowledge.
I don't have a question, but the gentleman over there was querying the effect of the weight of the car on road damage. I have done a considerable amount of work on this, and the road damage done by an axle is proportional to the force power of its weight, so that a heavy vehicle, an HGV, will do about 100,000 times as much damage as even the heaviest electric car. I don't think we need to worry about that.
Can we have a last question, perhaps? Well,
So you work for MG?
Yeah.
Yeah. So MG have a car is one of their cars is the car of the year. Is that because of its electrical properties, or why is it so good?
So the one reason is I'm using for a year, and the outcome or the mileage are the same as the day I bought. So the year of car depends on several factors, but majorly it should give you the same mileage within a year. So from starting, if you buy, maybe if it gives the mileage of 300 or 280 miles in full state of charge, so after 1 year it should not be less than 10 or maybe 5 miles. So that means the percentage is very high. The reliability, they are reliable to be used for longer.
Hi, I just wanted to ask, is there a preference on battery shape between America, Tesla, the European manufacturers and the Chinese manufacturers? Do they all have different battery shapes, or is there a dominant shape of battery that they use?
So these companies, they give you the battery shape, doesn't matter, but the material they use.